Hello everyone, I am Manisha from IIT Roorkee. I am in BTech third year, EPH. Today I am presenting on this is my AI/ML project, and my title is Comparing LoRa and Standard Fine Tuning on ResNet50. I have applied this on Galaxy Zoo dataset for real world image classification. Let's see our objective of this project. So this is the objective of my project. Our goal in this project is to compare traditional fine tuning and LoRa based fine tuning on the ResNet50 architecture for Galaxy image classification using the Galaxy Zoo dataset. We will evaluate them on metrics like accuracy, precision, loss, F1 score, and training time to assess both performance and efficiency and highlight how LoRa can serve as a powerful generalizable AI approach for efficient image analysis tasks beyond astronomy. Let's move to our next slide. So, why this project? Why this project? Fine tuning, because fine tuning large vision models is computationally expensive and requires a lot of memory. LoRa, which is low rank adaptation, offers a more efficient alternative that reduces the number of trainable parameters while maintaining or improving accuracy. While LoRa has been widely used in NLP and diffusion models, its application in astronomy, particularly in galaxy classification, remains relatively unexplored. Hence, this project aims to bridge that gap. Let's move to our the core idea of the whole project, the basic overview of the project. So the core idea is simple. We start with ResNet50 pre-trained on ImageNet, use it as a base feature extraction, and then fine tune it using two methods. First, simple fine tuning, and then second, LoRa fine tuning. And then we will compare both models on the basis of their metrics like accuracy, F1 score, and training time. Let's see what are the tools and libraries that I have used in my project. So for the implementation part, we used Python as a main programming language. We worked with several essential libraries, TensorFlow and Keras for building and training our deep learning models, NumPy for efficient numerical operations, and MATLib for visualizing results. Additionally, we use the PEFT or parameter efficient fine tuning framework to implement LoRa, which allowed us to fine tune our model efficiently with fewer trainable parameters. And we have used Google Colab to do the coding. Let's see our data set that I have used. So in my project, I have used Galaxy Zoo dataset. The Galaxy Zoo dataset, it is available on Kaggle Challenge. It's a large-scale astronomy dataset designed for galaxy morphology classification. We worked with two main subscripts, the training set, which contains around 61,578 labeled galaxy images in JPG format, and the test set, which has around 79,975 unlabeled images. Each image is annotated with 37 morphology categories, which are basically probabilities that describe the galaxy's shape, things like whether it's smooth, has features, edges, or spiral arms. These labels were generated through crowdsourced volunteer classifications, meaning thousands of volunteers helped categorize galaxies based on their appearance. Each image in the dataset is also linked to a unique galaxy ID, so we can track and map results easily. The dataset include two main folders. First is image training for labeled training images. The second is image test for unlabeled test data, and a file called solutions training.csv that contains the 37 probability columns for each training images. We also have a benchmark submissions available to compare our model performance with our existing approaches. So next slide is the pre-processing flow, which we followed before training our models. Our process followed 5 main stages. First is loading the raw images, then the label filtering, and then splitting our data set, and then transform, and then tensor. First is loading the raw images. We begin by loading the Galaxy Joe dataset, which originally contained images of Galaxy along with a CSV file describing their morphological classification across 37 different categories. Each image came with probability representing how likely it was to belong to certain galaxy types. Second is label. Since our experiment focused on a simpler binary classification task, we converted the dataset into two main categories. Uh, One is elliptical and the second is spiral. To achieve this, we used probability thresholds from the dataset. If the probability for class 1.0 example, if the probability for class 1.0 elliptical was greater than equals to 0.8, we labeled it as elliptical. If the probability for class 1.2 is a spiral, um, was greater than equals to 0.8, we labeled it as a spiral. If neither condition was met, we marked the galaxy as tie. After labeling, we noticed that the data set was imbalanced. One class had far more samples than the other. To prevent bias, we randomly sampled 81,000 spiral galaxies and 8100 spiral galaxies and 8100 elliptical galaxies, creating a balanced data set of 16,200 images. This system ensured both categories contributed equally during training. And let's talk about the splitting, how I split in my data set. This is a slide of that splitting data set. So we split a dataset into training, validation, and testing sets using the split folder dot ratio library, maintaining a ratio of 70 to 15 to 15 ratio. We have maintained 70% training data, 15% validation, and 15% testing data. This means this guarantees an even class distribution across all splits. This process ensured that both galaxy classes were evenly distributed across all subsets, maintained data integrity with no overlap between sets, and provided a strong foundation for model training, tuning, and unbiased evaluation. See, next, transform. Before feeding the image into the model, we applied several transformations like resizing all images to 224 by 224 pixels, normalizing pixel value to the 0, 1 range, and applying augmentation techniques such as random rotation, flipping, and zooming to improve the model generalization. And then tensor. Finally, we converted the pre-processed image into tensor flow tensors using the image dataset from directory utility. This function automatically reads images from folders, infer their class labels, batches them efficiently, and prepare them for GPU acceleration. Together, these steps load, label, split, transform, and tensor create a clean, balanced, and ready to train dataset for our tuning, fine tuning, and LoRa based models. Let's see the code for data pre-processing flow, then we will see our model. So first I downloaded my dataset using this command. These are all my input files. This is training, image test, image training. These are datasets. I splitted those dataset. I labeled them into two folders, elliptical and spiral, which I have already told. This is the condition which I mentioned, that greater than equals to 0.8. If the class 1.1, then that is elliptical or spiral. I mentioned it. Or else if 0.8, then then it's classified as tie. 8100 random sampling, 8100 spiral, 8100 elliptical to maintain balance. This is this this data set got spiral like this. And then we organized it into specific folders like um, image training, train images. I mean, it was originally in images training data folder. We organized it into train images folder. This is I have used the library split folders dot ratio to split the dataset into this ratio. And this is the code for converting images to the to tensor. Here image size is resized at 256 256. We have transformed the image sizes here. And we in the Galaxy dataset directly we made three different folders in which one is train, one is validation dataset, and the another is test dataset. And this I have plotted this picture. These are the picture dataset I have. Some of the examples of those dataset. Now let's talk about our next. So this is now let's move on to on the ResNet50 architecture, which forms the backbone of our model. ResNet50 is a deep residual neural networks that consists of 50 convolutional layers. It's on one of the most widely used architecture in computer vision, thus because of its strong ability to extract hierarchical visual features from images. One key reason for choosing ResNet50 is that it's trained on ImageNet, which is a massive data set with over a million ranges across 1,000 categories. This pre-training allows model to learn generic visual features such as edges, textures, and object shapes, which can then be transferred effectively to a domain of galaxy morphology classification, which this we can use in this data set. The core innovation in ResNet is the use of residual connection, also called skip connections. This is the uh, architecture core. Skip connection. These connections allow the network to skip certain layers by directly adding the input of a block to its output. This design helps in two major ways. First is it prevents vanishing gradient problem which often occur in very deep networks, and the second it enables efficient training of much deeper architecture without losing accuracy or stability. Because of this, ResNet50 as a robust baseline model for serves as a robust baseline model for feature extraction. In our project, we leveraged its pre-trained convolutional layers to capture the complex structure and textures present in Galaxy images, making it an ideal starting point for both standard and LoRa fine tuning. This is the flow diagram of our architecture overview in input layer and then convolutional max. There is a residual block and then the fully connected softmax output here we will get. Okay, so first is our first model is our ResNet50 frozen layers. This is our baseline model. In this setup, we initialized a network with pre-trained ImageNet uh, weights, meaning the convolutional layers already contain strong feature representations learned from millions of natural images. To preserve those powerful we froze all convolutional layers. In this, we freeze all convolutional layers. This means that their weights were not updated during training. The freezing means their weight will not update during um, training. As a result, the model relies on generic features like edges, gradients, and textures that is already knows. Instead of trying to relearn them from scratch using our small galaxy data set, on the top of this frozen base, we added a custom classification head designed specifically for our two galaxy classes, elliptical and spiral. The head consists of this a global average pooling layer which reduces spatial dimensions and summarized each feature pattern, and finally a softmax output layer which produces probability for two output classes. This frozen setup serves as a baseline model. It leverages journal ImageNet features but does not adapt to the unique characteristics of Galaxy images. So while it performs decently, it's limited in capturing domain-specific patterns, and that's where fine-tuning approaches like Standard and LoRa come in. Let's see our implement in code. So this is our ResNet without fine-tuning code. I've told this is uh, first. This is our global average pooling 2D activation. We have compiled it. We have measured only accuracy here. This is a custom callback that we have added to our code. In this, we have freezed all the layers. Now, let's move to our next model, which is model 2, which we have used in our code, standard fine tuning. After establishing our frozen baseline model, the next step was to make the network more adaptable to the unique patterns of galaxy images, and that's where standard fine tuning come in. Here we start with ResNet50 initialized with same thing that we done before this. But instead of keeping all the network frozen, we unfroze last 10 layers, we unfroze it. These deepest layers are responsible for detecting more complex high level features, things like texture, contours, and shapes that are spatially relevant for differentiating between spiral and elliptical galaxies. The lower levels remain frozen since they capture general visual patterns such as edges or color gradient that are universally useful across most image domains. This helps us retain the strong base representation from ImageNet while adapting only the top layers to our specific task. On the top of the network, we added a task-specific classification head composed of global average pooling layer to condense feature maps, and second is a dense layer with 1024 neurons and ReLU activation to learn domain-specific features, and the final softmax layer for classifying galaxies into two categories, elliptical or spiral. For training, we use the ADAM optimizer. For training, we have used ADAM optimizer. Yeah, ADAM optimizer with a low learning rate of 10 to the power minus 5, which ensure smooth and stable updates without destroying the pre-trained knowledge, a problem known as catastrophic forgetting. Overall, this standard fine-tune approach allows model to adapt pre-trained features to galaxy morphology while maintaining the stability of the earlier layers. As a result, it achieves higher accuracy than the frozen baseline by learning features that are more aligned with astronomical data. Let's see our code implementation of this. So from here, our ResNet with fine tuning has started. Here, we can see that we have la unfreeze the last 10 layers. We have unfreeze. This is our model head, global average spooling, and this is our dense layer, and this is our output layer, soft mix. We have compiled it. We are measuring precision, recall, and that top three categorical accuracy. And we have also measured the while fitting how much time it takes. We have measured this also. We will see the standard fine tuning result we can see here. This we can say this is our evaluation result and this is our validation result. Accuracy is we got 97.6% accuracy evaluation result, and the validation accuracy is also similar. Our total training time it took is 14.02 minutes. Took 14 minutes for whole model to fit. And this is our standard fine tuning result graph. This is our training and validation accuracy. And this is for loss. We can see our validation loss. It has increased and then decreased. Okay. So next is our model 3, which is a LoRa fine tuning model. Let's first see what is a LoRa. So let's see what is LoRa. Its name is low rank adaptation. Low rank adaptation. So now the idea behind LoRa is simple yet powerful. What is the idea behind it? Let's see. Instead of updating millions of parameters in the pre-trained model, LoRa keeps the original weights frozen and introduces a few small trainable metrics called low rank adapters into selected layers such as convolution or attention layers. These adapters learn the necessary adjustment to adapt the model to a new task. So rather than changing the main model directly, LoRa learns a small delta, a lightweight update, which is then added to the frozen weights during training. This approach drastically reduces the number of trainable parameters, which means low memory uses, fast training, and less risk of overfitting, all while achieving accuracy comparable to or sometimes even better than full fine tuning. LoRa has been widely used in large language models and image generation models, but it's still quite new in computer vision applications like galaxy classification. That's why I'm doing this project. So in our project, we are exploring how well LoRa perform compared to standard fine tuning when applied to ResNet50 for galaxy image classification. This not only demonstrates LoRa's efficiency but also tests its adaptability in a domain that's less explored in AI astronomy. So we have seen what is LoRa. The next step is how it works. In the standard fine tuning, we directly update the pre-trained weights W of a model, which often means millions of parameters being changed. But in LoRa, we do something smarter. We freeze all the original pre-trained weights, meaning they remain completely unchanged during the training. We already saw this in the previous slide. Then in selected layers like dense or convolutional layer, we insert two small trainable matrices A and B. We can see the graph here. Here uh, we are training A and B. These two are training. Matrix A reduces the dimensionality. It projects the large weight space into a smaller low ranked subspace matrix B remain, then bring it back up to its original dimension. During training, only A and B are updated. The rest of the model stays fixed. When we combine these adapters with the frozen weight, the new effective weight become this W plus A into B. Here W is the original pre-trained weight and the A cross B represent the learned adjustment, a small but powerful fine-tuning component. This way, the model adapts to new data or a new task without modifying its core parameter. It's like adding a small plug into module that fine-tunes the model behavior efficiently with much less computational and GPU memory uses. In our implementation, we applied these LoRa adapters to the convolutional layers of ResNet, enabling the model to adapt to galaxy images with minimum additional parameter. Let's see the code for this. This is our ResNet with LoRa fine tuning. This is our LoRa layer. Everything is same. All the code is same. And this is a summary. And here also we have imported time. Or we can see its a result. We have seen the implementation. Now let's see the result. These are the LoRa results. Accuracy, validation accuracy, we can see loss, precision, recall. Here the total training time is 9.16 minutes. This is our graph. We can see this. It's going smooth. This is our comparison summary. We can see that our standard fine tuning is taking 14 minutes, but whereas the LoRa fine tuning is taking 9.16 minutes. Accuracy is almost comparable. Here we only last 10 layers were unfrozen. Only small LoRa matrices A and B were getting updated. We can see computation cost here. It's high. Here it's low because training time and the trainable parameter is also less. And the training time is fast, so computational cost is low, and the memory uses also is less. So after seeing this, nonetheless, next thing that is the worthy to talk about is why LoRa wins uh, comparative to our standard fine tuning. The first is, let's first talk about the faster conversions. Since LoRa only adapts small low rank matrices instead of retraining millions of weights, it learns new tasks much faster. In our case, that required fewer epochs to reach optimal accuracy. Second is low GPU memory uses. Only the adapter layers are trainable. This means the GPU doesn't have to store or back propagate through all the parameters of ResNet50, making training lighter and more resource efficient. The third is fewer trainable parameters. Uh, The number of parameters update is drastically reduced, often less than 1% of the full model. This reduce translate to faster computation and lower energy cost, which is extremely useful for labs or students with limited hardware access. And finally, shorter training time we see. In an experiment, LoRa completed training in 9 minutes compared to 14 minutes for standard fine-tuning. That's roughly 35% improvement in speed. Now, coming to performance, even with its lightweight setup, LoRa maintained comparable accuracy. It achieves 94.98%, just slightly below 97.61 we got from standard fine tuning. Precision and recall, we all saw, remain consistently high, both around 95%, showing that the model generalizes well without overfitting. And then what's also impressive is its stability during optimization. Since the pre-trained backbone stays frozen, there is no risk of catastrophic forgetting or losing the knowledge from ImageNet training. Lastly, scalability. LoRa can be easily deployed on limited hardware setups, even on a single GPU, without sacrificing performance. So overall, LoRa demonstrates that with smart parameter efficient design, we can achieve high accuracy at a fraction of the cost and time of standard fine tuning. Now let's see the conclusion. Finally, to conclude, the key takeaway from this work is that LoRa significantly reduces the cost of training large vision models. Instead of retraining all model parameters, LoRa only updates small, low-rank adapter layers, making it far more efficient. This approach improves fine-tuning efficiency in multiple ways. It allows for faster conversions, lower GPU memory uses, and shorter training time, all while maintaining comparable accuracy to standard fine-tuning. Our experiments showed that ResNet50 continues to perform strongly even when only lightweight LoRa adapters are trained. This highlighted deep networks don't always need full-time tuning to adapt effectively. Sometimes a focused and efficient approach can deliver nearly the same results. In summary, LoRa stands as an optimal method for resource-constrained environments, enabling powerful AI model adaptation on limited hardware without sacrificing quality or stability. So this experiment not only validate LoRa's potential in galaxy image classification, but also demonstrate that how parameter efficient fine tuning can make AI more accessible and sustainable in practice. This is my from my side. Let's go through the code once again. So I downloaded this first. I downloaded my Galaxy dataset, and then I stored it in this folder. These all were the dataset that got downloaded, and then I installed split folders and path library to split my dataset into different folders. This is my basic framework. All the libraries and framework that I've used in my uh, code, TensorFlow, Keras, split folder part libraries, this is image generator, matplot library, pandas, numpy, math, which we have used here. We have used from layers, tensorflows.keras.layers. We have been that convolutional 2D, max pooling, latent, and these all functions that we have used in a model. And we unzipped these where our training and trained images and the image training files were stored. This is the how our data was, and then we put here we put condition to classify those all the labels into two categories, elliptical and spiral. That's why it's like this. Some are spiral, some are elliptical. The total were spiral 8100, elliptical 8100. We did this using this code so that random sampling so that our data set would be balanced, no bias. Then I organized my images into specific folders. Like all the images I stored in the train images, so it would be easy to for the training. And then using the train images, I use this train images, and then I using split folders, I divided it into 70, 15, and 50% ratio. Here I have converted these images into tensors. Image size I set it to 256 to 256 pixels, and in 3 folders I have uh, divided my data set: train, validation, test, which we have already seen. Picture some of the examples we have here plotted. And this is our code which we have already seen, ResNet without fine tuning, where we have frozen all the layers. This is our base model, head of the model. A learning rate, this is our metric accuracy, and we got custom callback. Accuracy we got just simple with simple fine tuning was 70%, and this is the loss. And this is our with fine tuning where we unfreeze last 10 layers, and else we remain it frozen. Same model setup. Here we compiled it, and we uh, measured precision, recall other than accuracy, and we also measured time, how much training time it takes to run to fit the model, and this is what we got. We have plotted here. We have uh, printed like accuracy 97%, losses this much, and training time 14.2 minutes. Here we have done validation result. We have printed validation, how well it is performing on validation dataset. So this is our validation result, and this is our graph. And this is the code with LoRa fine tuning, as we have already seen it. I will go through. Here we are just um, uh, tuning only two parameters A and B, not all the weights W. The else code is same only. Same we have measured same things. Training time we have plotted here, 9.16 minutes. Merge LoRa weights, and we have saw that W equals to new weight equals to W plus A cross B. That is this thing. And we have evaluated. This is our evaluation result, and here validation result. In this code we have plotted. This is all. Thank you so much for seeing my video.